Now I know some of you are not big fans of geometry, but I think it is important to understand some of the maths in calculating how many pulses there are in a degree of the rotating robot. And so I want to show you kind of how you would jump through the geometrical steps to understand that with our little robot. Now the robot is 18 inches across on the side. So it's tempting to make it a problem that involves two 18-inch sides, but the reality is that the wheels themselves are 4 inches on a side, which means that we have to come in 2 inches from the top and the bottom to actually get to where the center of the wheels are. Now this is a rough estimate, obviously. I'm not taking into account the width variation, but we're going to say that this is an 18 by 14 inch rectangle that we're going to be rotating. When we rotate it, we end up with something that would look like this. Now, how do we know what the diameter is? We need to know the diameter so we can get the circumference. Well, if you look at it, it is actually an 18 by 14 by something triangle, right angle. Therefore, we could use the Pythagorean theorem to understand what the hypotenuse would be. That means that the hypotenuse would be the square root of 14 squared plus 18 squared. Now hold on, because it's going to get a little bit ugly, but we're going to run through some of the calculations to try to figure out what that would resolve to. 14 squared plus 18 squared is pretty much the same thing as 2 times 7 times 2 times 7 plus 2 times 9 times 2 times 9. This is important because we can extract out the 2's. And what we end up with is 4 paren 7 squared plus 9 squared. We know the square root of 4 is 2, and so we can pull that out. So it's 2 times the square root of 7 squared plus 9 squared, or 2 times 49 plus 81, or 2 square root 130. So now we know what the hypotenuse length is in inches. It's 2 times the square root of 130, or approximately 22.803508502 inches. That's great. Now we know what the hypotenuse is, and knowing that, we know that the circumference of the circle, the circumference of the route, is going to be 2 times the square root of 130 times pi, as if it could get any uglier. Well, here's the thing. The wheels themselves that are on the robot are 4 inches in diameter, and therefore we know that the circumference of the wheels themselves is 4 times pi, or pi d, which is the same thing as 2 pi r. Therefore, the number of rotations of wheels that it takes to complete this circle is 2 times the square root of 130 times pi divided by the circumference of the wheel, which is 2 times 2 times pi. We can eliminate the pi from top and bottom, and we can eliminate one of the 2's from top and bottom, which tells us the rotations of the wheel are actually the square root of 130 divided by 2. Now the number of pulses in the wheel is 1440. If the route goes 360 degrees, the number of pulses will be 1440 times the square root of 130 divided by 2. The pulses per degree are going to be 1440, the number of pulses in the entire rotation, times the square root of 130 divided by 2, the number of rotations we're taking. All of this divided by 360, the number of degrees in the circle. Now the nice thing about this is that 360 actually goes into 1440 4 times. It's not a coincidence, that's how they set that up intentionally. The result being that the number of pulses per degree is 4 times the square root of 130 divided by 2, or, wait for it, 2 times the square root of 130. And if you look up toward the top, you'll see that that is the hypotenuse of the circle created in the rotation. This is not an accident. It has to do with the diameter of the wheel and the number of pulses being divisible by 360. But just so you know, that is actually going to be roughly the number of pulses per degree. And we'll use this in our maths. So I hope you enjoyed that. It's kind of a fun one.